I think one of the big achievements of array programming, for me, the big motivating thing is as soon as you have felt this thinking in terms of shapes, things become much clearer and you can express things much more concisely.
Welcome to episode 107 of Arraycast. I'm your host, Conor, and today with us, we have a special first-time guest. Very excited to get to talking with him in a couple minutes, but first, we're going to go around and do brief introductions. We'll start with Bob, then go to Stephen, and finish with Marshall.
I'm Bob Therriault. I am a J enthusiast, and I'm going to have my mind expanded today, I think.
I'm Stephen Taylor. I'm an APL enthusiast, and I think my mind might get a little discombobulated.
I'm Marshall Lochbaum. I'm very worried now, but anyway, I started array programming in J. I worked at Dialog for a while, and now I develop BQN.
And as mentioned before, my name's Conor, host of Arraycast, massive fan of all the array languages, and excited to talk about one that has only been mentioned a few times. I know it's been mentioned on the podcast, but I don't think we have dived deep into it at all. And we will get to that right after this introduction, because we have zero announcements today. So we're going to go straight into introducing our guest, who is Sven-Bodo Scholz, a professor at Radboud University. Hopefully I'm pronouncing that correctly. I did watch a YouTube video of an English student there, and it looks like a very beautiful campus. But he's a professor in the Department of Software Science of the Institute of Computing and Information Sciences. But for us, he is the individual behind SAC, that is Single Assignment C, which, like I mentioned, is if you are an astute listener with a very good memory, you will know this programming language as a functional array, kind of C-flavored programming language. I think we've mentioned it on a handful of episodes. I won't be able to recall which ones, but Bodo has been on my list of folks that I've been wanting to get on this podcast for many months now, and we're extremely excited to have you here, Bodo. So maybe we'll start off by just throwing it over to you. You can take us back as far as you want to when you started getting into computers or programming languages, and along the way, I assume at some point you discovered the array language paradigm, and then take us all the way to today, 2025, and the research that you're doing with Single Assignment C and everything related to that. So take us back as far as you want.
Yeah, well, thank you very much for having me in the first place. It's a big honor to speak on this platform and share a little bit of my journey here. Where should I start? I could potentially start essentially when my brother started building one of the first computers at home, where I thought, "Ooh, this is cool stuff." It is also, so I have a little bit of a hardware taster there. And then it was clear I have to study computer science. And in computer science, the first thing I was exposed to was lambda calculus. And I thought, "Ooh, this is a cool thing." And I had already, self-taught, the typical stuff that you would know, a little bit of BASIC, a little bit of assembly, that kind of thing. And then I realized, oh, look, most of the stuff you can actually describe very nicely. And it was also clear you have all this wonderful concurrency that is built into the semantics. You can evaluate in any order, and the result is never going to change. Oh, no more bugs. That sounds cool. And I kind of got hooked into this story, and I thought, oh yeah, we have to have parallel performance. Really, this is what we have to do. And then I started doing this in the context of my diploma thesis, which is kind of a master thesis at the time in Germany. And I was super proud. I could, had wonderful speedups on Quicksort, almost linear speedups up to 16 cores, which at the time, is like late 80s. It was amazing that we had a machine like that. And it was a super expensive shared memory Spark station. And I was proud like nothing else. And until one of the PhD students in the department came along and said, "Oh, well, but that's good speedups. That's amazing. What's your absolute runtime?" "Oh, yeah, it's, I don't know, it's like, 10,000 elements or something." And then they said, "Oh, yeah. And how much time do you need?" "Yeah, 10 seconds. And I said, "Well, you are aware that if I use a sequential C version, it just takes a fraction of a second, right?" And that was, for me, that was like, it was, facing the brutal truth. It's like, okay, the way we do functional programming sucks. I mean, it is great, but we don't get the parallel performance, right? How do we get there? It doesn't even make sense. Well, okay, it became clear the baseline has to be fast. And how do you do a fast baseline in the functional setting? And if you look at the typical functional languages, then you have lots of frills, which are great. You have lazy evaluation, garbage collection, algebraic data types, all these super fancy things, advanced type systems. And when you try to implement them, you figure out, ooh, you have to start boxing data, you need garbage collectors. Ooh, you can't predict what is going to be evaluated. Debugging is a problem. Higher order functions. You have to build closures. Oh my God, this is way too costly. We can't go there. So this is what kicked off my PhD studies ultimately. And then I came into touch with Leonora Mullen. Her work on the psi calculus, which was trying to formalize essentially APL. It was called Mathematics of Arrays, and I was reading her PhD thesis, and I thought, "Ooh, this is kind of cool stuff." And also, it gives you the opportunity that you can do, real parallelism, data parallelism. What can possibly be difficult about data parallelism, right? Yeah, and this is one of the things that kind of haunt me, and to the day, very often, if I tell people what I do, they say, "Oh yeah, data parallelism is simple, right? You just everybody knows how to do a map." Right? What can be possibly inefficient about that? It turns out it is much harder than one might believe it to be. And so that was kind of the birth of the idea of SAC. So the idea was to say, okay, I want to have a functional language, but it should be easy for the people that do data parallelism. So maybe something like C is a good idea. So that gave me the first hurdle, because people say, C and functional programming, you got to be nuts, right? You got to be out of your mind, right? How can C be functional? And my claim, which I hold up to this day, is that, yeah, C is a perfectly functional language as long as you don't use pointers, which is kind of a cruel statement, but essentially SEC is just that. It is C, but it doesn't have any pointers. It doesn't have any notion of memory. It just has arrays. Every data structure is a potentially n-dimensional array, and you can define C functions that take arbitrarily shaped, and that includes ranked arrays as parameters. So that was the basic idea, and you stick to that until today. But then the question is, which combinators should we have? And then I detected the wealth of the world of APL, but I also came across a few different people. So at the time, that was like in the 90s, early 90s. I was meeting people like Bob Bernanke. I was meeting David Liebtag. I was meeting the guy from APL 2000 New York, Brown, I think. Jim Brown, yes. So I was meeting all these folks, and they told me, "Oh yeah, you have to do, you have to have a rank operator, or you have to do this, and you have to do that." And they all were absolutely convinced that there's a certain set of combinators that you have to support. And I thought, yeah, they are all convinced of one particular set, and what set should this be? And also, if I ever want to optimize this, well, then I have to look at I have to pattern match for phrases. Oh my God. And I have to teach every phrase to my optimizing compiler, because remember, my driving force was performance, right? So essentially, I think the only kind of, one of the two ideas that are in my PhD thesis is to say, okay, I don't want to have any fixed operator, but I want to have a language where I can define any operator the way I want it. And if I define it by a single, albeit a little bit complex language construct, then all I have to do is, when I have a combination of these, I have to be able to kind of hold them together. I have to be able to fuse them into a single operation. Because one of the key things is, if you materialize intermediate arrays, your performance is doomed. So I have to be able to fuse operations, and I don't want to teach my compiler, I'm way too you could say lazy to implement this. I don't want to teach my compiler all the phrases that I need to recognize. I just want to have essentially combination of one and the same language construct. And ideally, the transitive HAL of these can be expressed by this operation as well. And that was the key of the SAC journey, where we started and where we could show that you can write something in very much APL style and still get the C-like performance out of it, just in the sequential case even. And at the same time, because it is a side effect-free language, you also get all the benefits of the concurrency that is semantically guaranteed, and that is really nice. So, if for example, if you think about C and you have OpenMP, then you can make annotations and tell the compiler, yeah, it's all good. But, I tend to teach these things my students, and the students, when they get it wrong, they are really happy to have fantastic runtimes, but unfortunately the results are often wrong because they have a race condition, some annotations are wrong, and there you go. So that's why I kind of stuck to this. I had a couple of journeys into different ventures. I looked at stream processing at some point in time, but I always came back to SAC because I'm still intrigued by the design, but kind of the simplicity in the design, and the ability to express arbitrary things, to define your own combinators, to combine the combinators without being punished in terms of performance, because there is no guarantee that any intermediate array that you specify is ever going to materialize in memory. So I've become an increasing believer into this. And then, the question was, how far can you push the performance, and how far do you have to change the code if you target a different platform? So currently, we started out doing shared memory multiprocessor systems. And so this has been done by Clemens Grelk in the 90s, fantastic work, very good performance. Then in the 2000s, Jingguo built a GPU backend for us. And then we found out, some of the optimizations we typically do are not good if we want to do GPU stuff. So actually, our compiler is, you tell the compiler what platform you want to generate it for, and then different things happen under the hood. And the good news is the source code does not change at all. You can use the same source code for sequential, multi-threaded GPU cluster, multi-GPU, whatever you want. But with, not always, a black belt performance, I would say. But in many cases, very close to black belt performance if you do this smartly. And now always, one of the things that I'm particularly, how should I say, enthusiastic about, maybe that's the right wording I should choose here, is a discovery that I should have made 20 years ago, but I essentially made last year. And that is a good answer for the question, why do you need rank polymorphic programming facilities? Right? Because, traditionally I said, rank polymorphism is great. You can define these combinators. They are applicable to arrays of any shape, dimensionality, no limits. But then people come back, but all my applications have at most 4 or 5 dimensions. So what is it good for? And I then said, but if you need one more, you can get it automatically. But lame answer. And I had to give it to them. And I was pretending that, I still thought this is a big leap forward. Now, fast forward to last year or the year before, I had this experience with one of my PhD students, and he, came from numerical computing and completely outside the computer science realm per se, but he comes from mathematics. And he says, let's do matrix multiply. Okay, he did a naive matrix multiply, as you do in array languages. It's a 2-liner. Very nice, very close to the mathematical specification, but slow. No, sure, it is slow because everybody knows, it's a cache problem, so you have to do tiling. And then he came into my office and said, Bodo, this tiling really, forgive my French, sucks in SAC, right? Because, you don't really want to write loops, and the language is not really made for this, and man. So, but I'm kind of stupidly proud a little bit about the language design. So I thought, okay, I have to give him a good answer on this one. So, hey, conceptually, if you tile, isn't that just, kind of creating a higher dimensional array. So instead of having a two-dimensional matrix or two-dimensional matrices that you multiply with each other, actually it is a four-dimensional matrix multiplied with another four-dimensional matrix. And then what you do is you have a matrix multiply on the outermost two axes, and instead of multiplying the elements, you do a matrix multiply on the elements, which are two-dimensional arrays. Clear, easy to understand in an array programming setting. So this is now a recursive function. It is a rank recursive function. You want to have like 4 or 5 levels of tiling? No problem. Make it a 10-dimensional matrix. Two 10-dimensional matrices with the matrix multiply. And, he went away and, said, oh, yeah, it's great. I get the right results. Oh, yeah, that's good. And then I was afraid what was to come, because I thought, oh, my God, rank recursive functions. If I think about what kind of code and open, no, I'm not sure I want to see that. Monday morning comes, he comes into my office and says, oh, no, this is great. It works, but it is so slow. And I thought, yeah, I expected that he would say something. Yeah, I get like 2 gigaflops because, yeah, well, this is roughly what you get on the naive one. And he says, oh, I only get 60% peak. That is like 400 gigaflops on my laptop. I said, what? Yeah, I think it should be more. So I really like this attitude, right? And sure as hell, he figured out what it was. And, there is a problem of the C compiler not being able to deal with the innermost loop. So he created some inline assembly. And, we replace one explicit loop by, we have an explicit definition for a particular size in the code, and then it all works, and we get like MKL-like performance. But the specification is actually, forgive me for saying so, is really sexy, because it is, I have one specification for n-dimensional tiling. And if you look at the packages that you have in standard, MKL or OpenBLAS or whatever, they have thousands of lines of code. And why do they need this? Well, because they have various different blocking scenarios for various different architectures, and depending on the architecture, they use a different blocking. But this all sits in the code. If you have rank polymorphism, as we do in SAC, then it can sit in the data. And the compiler, if you tell them the compiler, what's the shape that you throw at it, the compiler can go clonkety, 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 clonk, and generate your tiling. And to make matters even better, if you trust your code generator, then actually it's guaranteed to compute the right thing. So one of the things that we have done is we actually have encoded this in Agda and proved that our rank polymorphic version is guaranteed to compute the same thing as the naive one, which essentially means, you can tile any which way you like, and it's guaranteed to do the right thing, assuming that the code generator is working, and you can get excellent performance. So that's where you need rank polymorphism for. Because rank polymorphism allows you to kind of encode in the shape the way you want the data to be traversed. And that is the key thing if you want to get performance. That is the key thing for locality that you can steer. It is the key form for you can also shape if you have a fixed layout that your compiler produces, as we do row major, then you can actually kind of influence what happens also with the parallelism. Where does the compiler actually decide to generate parallelism and where it doesn't? So we also applied this for scan, which is also a very cool solution, because you can have a rank polymorphic version of scan, which if you choose the argument to be a vector is purely sequential, but if you choose the argument to be a higher dimensional thing, you get a parallel version. And in fact, if you choose the shape to be a power of 2, so to speak, so a 2 by 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 2 thing, then Blelow's algorithm falls out for free. You just have it. And you can choose this. And potentially a compiler could choose this, but in essence, you can choose this and play around with this. So that really got me into this. I have a better answer now, right? If somebody's asking me what you need rank polymorphism for, I tell them it allows me to actually express essentially an entire class of algorithms that compute the same thing, but depending on the shape, have a different memory or concurrency behavior. And that is super powerful because I can reason about these programs. I can run, mathematical proofs about what they do, whether they're correct, whether they're equivalent, all these things. Now, after we have done this, obviously the next painful thing that arose was we have our type system was always driven by partial evaluation. So we said, okay, we have to talk about types, right? Because if you want to generate code, you better know something about types. And we want to figure out whenever we are dealing with scalars rather than just arbitrary arrays, because then we don't have to box them, we don't have to dynamically allocate them. And actually, we try to get everything into static shapes as much as possible as we can. But our type system does not allow to express full dependency on shapes. But if you write rank polymorphic or rank recursive algorithms like the ones that I'm talking about, this becomes really painful because it becomes very difficult to understand whether you're dealing correctly with your shapes. Because thinking recursively about shapes is a bit funny. And if you get this wrong, it is rather painful as well, because you get some runtime error and say, oh, you have an out-of-bounds selection here because we couldn't statically infer it. Yeah, because you didn't provide enough information about your input. Yeah, so what the other step that has happened that has just gone into the version of SEC 2.0 is that we have provide now type pattern. And the type pattern allow you to specify relationships that you expect on arguments of your functions. So if you have a naive matrix multiplier, you just say, okay, it has to be a double MN and a double NK. But we allow arbitrary mixes there. So you can say, if you have a take and you say you have a scalar integer parameter int n, then you can use this n, the parameter name, within a shape pattern as well. So you can describe all kinds of relationships, and in particular, you can also do this for these rank polymorphic things. We try to partially evaluate these things. And if we can't partially evaluate it, you can decide whether you want to have a runtime check or not. So while you're developing, most likely you want to have these runtime checks. But if you are confident about certain functions, you may just suppress the runtime checks in those functions and get potentially better optimizations for this thing. And that's why I'm very excited now about this, because I think this is also a good opportunity to really make a difference when it comes to, say, implementing like deep learning networks, because you can specify what the shape requirements are. And that means you can also more easily debug your programs, because if you assume that you specify all your domain constraints on every function, you will get the outermost failure. So if you call matmal with incompatible arguments, the compiler will say, oh, you called matmal and, the type patterns don't match here, rather than something deep down in the call graph saying, ooh, this is out of bounds now, or something like that. So yeah, it has actually shifted my perspective a little bit. And I'm excited about many new developments. Also, the arrival of these billions of new accelerators where we can generate code for, and heterogeneous systems. We just started playing with one of these Intel systems where you have two different kinds of cores in there. Then you need to have a code generator to really make good use of that. And there's many more things I'd be happy to talk about, but I think I really need to give you guys an opportunity to engage here, because there's a plethora of exciting things going on. We are creating new backends for new architectures. We are improving the debugging experience. This type system thing is getting increasingly exciting as well, and we have created how it's called, a Jupyter notebook plug-in, so we can pretend to be REPL, although we aren't. We just run the compiler in the background and things like that. So I know professors like to talk too much, so I will stop here for now.
It's all right. It makes our job very easy. That was, I was just queuing up the questions, and I'll do my best not to ask them all at once, and maybe I'll treat it as a stack. So we'll do last in, first out. You mentioned SAC 2.0. When I was looking at the docs just before recording this, I think on this website, it said that it was, or at least the docs there showed it for 1.4. So is there an upcoming 2.0 release that is like breaking news that we're letting our listeners know about?
Well, if you look at the open source compiler, the compiler already claims to be 2.0, but it is not yet stable enough that we are happy to really shout out about it. I hope that we will have a release party somewhere in autumn. We have most of the features in, but this type stuff is really new, and we also have support for structures now, so you can do. You can also have arbitrary nesting of arrays of structures that contain arrays of other structures as substructures, and that has created some new, has unleashed or unearthed, I should say, some new bugs that we have not been aware of, and we're trying to fix those things. So yes, it kind of exists, but we have not really widely advertised it yet. We are actually not very good at advertising ourselves.
That's all right. I'll keep my eye out for updates in the fall time space, and maybe we can announce it on a later episode when it's fully ready to be launched.
Very much appreciated.
Yeah, absolutely. Bob, you had your hand ready to go.
Yeah, Bodo, you mentioned Lenore Mullen and her mathematics of arrays. How closely does SAC follow that? I had a chance to talk to Lenore, probably a couple of years ago. Actually tried to get her on the podcast, but at that point, to be quite honest, I think when she talked to me, she realized I wasn't sophisticated enough really to deal with this stuff. I think we've probably, well, I don't think that's a bad read. I think she probably had a good read on that. But at that point, she sort of declined. I'm not sure she thought we were as serious as we maybe should have been taken at that point. But I think we've got into that zone by talking to people like you, Bob Bernecki, a number of other people that are really very deep into the same kind of design. But are you still following quite closely to her mathematics of arrays? Because I know that's something that's really, I would guess it's axiomatic to her. It's a axiomatic system of arrays.
Yeah, it is. It's kind of a longish story and not exactly an easy story. So I was very much inspired by her work. I think the Psycalculus is a very nice formalism. And so in a way, you could say that our key language construct, which still under the hood is what we call a with loop, although these days I try to avoid that terminology. We are now more about tensor comprehensions, just because we have a new front end, and I think it's much more readable. It's also, it's more expressive and things. But ultimately, internally, this is all mapped to these with loops, and they are very similar to her psi function, at least in intent. The difficulty that I always felt is that whenever I talked to Lee Malin about these things, then she very often, immediately fell back to her mathematical notations, and I said, look, I think we need to have a representation. Right? Because if you want to have a compiler, you need to have a representation of what you do. And maybe something like the with loop is a reasonable representation for this. And I had the impression that she considered my wish to have a representation and talk about a representation as being too mundane, maybe, or not really relevant, and that's where we had a little bit of a problem. And so I kind of see what she's doing, and I think this is still exciting, and it is good work. But I felt a little bit that it would have been nice if this would be more closely related to an implementation effort. So I would say there is a close relation, but it is, I think, while being very similar in spirit, the implementation is very different.
Yeah, as I said, from talking to her, I think she's a very strong person with very strong opinions about how things are done. I think that's what got her to the point of understanding this stuff and explaining it this way. But I can imagine if you were trying to put something into practice, you'd probably find pretty quickly that it diverges a bit from what her vision is.
Yeah, that is kind of that's kind of the situation as I read it. Yes,
I'll give another try to get her on because she is fascinating and brilliant. But as I said the first time, I don't think she only talked to me. She didn't talk to anybody else. So she was probably influenced by my naivety, I guess. I don't know. The other thing you were mentioning, you were talking about the rank polymorphism. That's really interesting because actually, when you're trying to talk to a person who's programming and you say, well, rank polymorphism is used for this, as you said, it was kind of weak sauce when you first talked to them because it's like, well, I wouldn't do it that way. That's a reason. But it's not that they would use it. It's that your compiler uses it.
Yes.
And that's the step that they don't even see normally. We had Henry Rich on the last episode talking about all the steps that an interpreter does that you wouldn't see when you're actually trying to program. But it's that level. By having rank polymorphism, it allows your compiler now to do things that the programmer doesn't even actually have to be aware of.
Yeah, I think it's also, I think one of the big things or achievements of array programming, or for me, the big motivating thing is as soon as you have felt this thinking in terms of shapes, things become much clearer and you can express things much more concisely. And so I think there's really kind of almost like a barrier that you have to push through. And once you've seen it, you can't unsee it anymore. And it becomes very natural. And you think, yeah, sure. If I talk about this, is exactly like the tiling thing. Once I had understood that, yeah, sure, tiling it's just higher dimensional arrays. That's all. And then all of a sudden, the specification becomes like a six-liner, and you have arbitrary tiling, and it's all there, and you can prove that it's correct. I think that is so sexy that you can't do it any other way. And if you have ever written a tiled code by hand, I think being exposed to this kind of style will give you the goosebumps. It's just amazing.
It's like finding a seam in something. Suddenly, it all just drops away.
Yeah, it is. It is a cool way. I think it's a bit like, you could argue, if you look at object-oriented programming, it's a similar thing. Once you start thinking about state as being encapsulated and representing a stateful thing, and then you have objects and classes. Yeah, it makes sense for a certain kind of thing. And the same holds if you want to massage massive amounts of data. It's a good idea to think in terms of shapes. And it also matches very well the scientific computation world. Like, if you just look at the physics papers or the mathematics papers, how they are written, and you can rewrite this in an array language, one-to-one. And I think this is really, really powerful. And I hope that this entire buzz about, machine learning will get more and more people to experience this joy.
Go ahead, Marshall.
First, I will say I did read the scan paper. I didn't see the matrix multiplication, but on scan, I thought that was a really good presentation of the idea, and I even referenced it in my own notes on implementing scan.
Oh, thank you.
The big question I have about this approach generally is when I'm writing like tiling code or things that generally work in chunks, it usually feels like there's the work is split into one part of figuring out how to chunk everything, and about 10 parts of figuring out what to do with the last chunk. which may not be a full chunk. So my question is kind of, you tend to describe these things in terms of, well, you just split the shape into factors and then it all works. What do you do if the shape is not evenly divisible?
Yeah, there is some more research to be done. If you allow me to answer that cheekily, yeah, that is clearly is a problem, and one of the things that you could think of is that you say, okay, I just pad my array, and I can, have a padding operator that then brings to a power of 2. And then the question is, how much will our standard optimizations already give you? So most likely the embodying into the zero padded array will come at almost no cost. Yeah, it is that is an open problem, and I obviously in an academic publication I like to sweep that a little bit under the carpet. But that is something that needs looking into.
Yeah. I mean, I guess the ideal from my perspective is in SIMD programming, at least, like the last dimension, you have to pad. You have to work in full vectors because there's no such thing as a partial vector operation. Like you can mask it, but that's just a full vector operation that you don't entirely use. What the ideal would be maybe to pad in each dimension. So there is waste, but there's very small waste. But that means you still have to deal with it's fundamentally not homogeneous because, like, if you have 2 dimensions, the last row of your matrix is not as long as the other rows. But the idea would be that by kind of doing that recursively, you get. I mean, I'm not saying that's actually a solution that works with your language or necessarily or compiler, but that's kind of a discussion point on how to approach it.
No, absolutely. I mean, there is where these are 2 different things in a way that you have mentioned. So this padding problem is indeed is a problem and requires a good solution. I would have some ad hoc ideas how to approach it, but it requires elaboration and finding out what needs to be done in order to get efficiency there. There's also the problem to figure out what kind of tiling you really want. Currently we were just kind of stealing this from MKL and Co. To just say, okay, they use this tiling, we use the same tiling, and we just do it in data, and that's it. That's one thing. When it comes to vectorization, that's actually another can of worms. And I had a PhD student in Edinburgh to work on this. So the key idea there was to actually transform the shape of a given matrix and with it the entire algorithm, so that you get in the last axis a vectorizable vector, and that is actually, the theoretical work was all done. There exists a partial implementation, but it is unfortunately not in our main compiler branch, because there were some missing bits and pieces, and then he ran out of time, and I couldn't find someone to pick up on this. And but that is also a very exciting field of work where you can say, okay, really, I don't want this in a column here. I want to split up this column into 2 axes, and you can have an array transformation calculus, which then allows you to transform the entire computation accordingly. And that is a very exciting piece of work, again, where helping hands would be needed to make this happen. Ideally, I would wish that we could derive these kind of rank polymorphic, rank recursive algorithms from the naive one.
Yeah.
Right? That you say, okay, I just use my matrix multiplier, and then the compiler goes, this looks like I should be, changing this into rank polymorphic one, and then I should reshape this, because it always boils down to the same thing. It is ultimately you have a reduction, and you want to make sure in which order you perform the reduction. And you build on the fact that we pretend that that actually our floating point numbers are proper fields. That all the laws to hold. I mean,
I've been writing some reduction code in BQN, and we do not assume that. And so, there's a lot of avenues that are closed to us.
Yeah, it is. And if my the PhD student who did the MatMol thing, Thomas, he is very much looking into numerical stability, and the more you start looking at it, the more fearful you get. It's actually almost like thinking, yeah, it's amazing that we get anything sensible out of this. Because it's very difficult to predict. It's very difficult to predict which order you should do summation, unless you know something about the distribution of your data. But you typically don't.
On the one hand, yes, but on the other hand, the sequential ordering is like one of the worst.
Yes.
So,
well, but then, which ordering is admissible and which one isn't.
Yeah.
And if you say, okay, I assume that the programmer knows it all.
And you're pushing a lot of work onto the programmer.
Yes. And this is just avoiding a blame that I think is unreasonable to expect from the programmer. The average programmer, that is, if you have a mathematician that is thinking about the stability of the algorithm, but even then, if you have a mathematician that thinks about the stability of an algorithm, then they will try to make it robust so that actually the order really doesn't matter.
Well, and they'll know that this is work that they absolutely don't want to do because it's very taxing and just really complicated.
One of the things I was hoping to get you to talk about more, Bodo, is you mentioned back in the 90s when you were talking to a bunch of folks and everyone had their own set of combinators or primitives that they said, oh, you gotta, this is the set, and everyone had a different set. And then, correct me if I'm wrong, but it sounded like you were talking about this simple, even though it takes a little bit to learn, language construct, which I think you were referring to the with loop / tensor comprehension. And so I'm hoping, you could maybe explain for our listeners a little bit about that. And also, as I was looking up with loop in the docs, I noticed that the keyword fold or keyword or identifier was right next in the identifiers. And I thought when I looked into single assignment C, I think it was 2-3 years ago, I was trying to see if there was a way to write a generic reduction that you could just pass a lambda or something, or binary operation. And at the time, I couldn't find one. You have all the sum, prod, min, max, similar to MATLAB and Friends. But now when I see this fold, I'm like, did I miss something or did something get added? So
yes.
Two questions at once, I guess.
Yes, you indeed miss something. You can pass an arbitrary binary function there. And then all the definitions for sum and prod, they are in our standard library. So essentially what we really have is we have a map construct and a fold construct, or a reduce. And you can fold them into one. So you can actually have this map construct is the with loop. And the with loop allows you to specify index ranges over which you want to map something. And it allows you to actually specify multiple results that you want to compute at the same time. And mainly that's it. And then you can change the mechanism to perform a reduction. So you can have index ranges, you can have multiple index ranges and say, okay, whatever values I get over these index ranges, fold them all into a single value. And then you can have this fold, so we call this an operator. So we have a fold operator, we have a generate operator and a moderate operator, all of which are, the former, generate and moderate typically perform just a map operation of sorts. Or as of recently, I'd rather speak about an IMAP, meaning it's an index mapping. So you specify an index range that never materializes in memory. It's just kind of a generator specification. And then you specify what it is you want to do with the values that you compute. And you can either put them into an array, or you can fold them using a reduction operation. And that's it. And it turns out, and that's the funny thing, is if you define an array A with this operation, and you define an array B, by using affine selections in A, you can always fold this into a new form of with lib. It's transitively closed. And that gives it the power that you can, as long as you have affine selections only, you can all boil it together into a single with loop. And that means you get rid of all intermediate arrays that way. And that's where some of the power comes from. So if you, for example, do a matrix multiply, have a result in C, and then you perform something like a stupid increment on all the elements, then the increment will happen while you compute the matrix multiply, because the two will be fused together. And I think there's the opportunity for array languages in general to even outperform highly tuned libraries. If you have libraries, then typically the library calls are, like walls of stone. You call matrix multiply, yeah, boy, it's going to be super speedy. But you have to materialize the full result in memory, and you will get it in memory, whether you like it, whether you need it. No. Even if later on you only do a take 10, 15 over a 10,000 by 10,000 matrix, yeah, sorry, the 10,000 by 10,000 matrix is going to be materialized in memory. And we don't have to do that. We don't have to do that. And so I think there's a lot of opportunity because we can do kind of arbitrary folding. Now, again, this is a bit of an oversell, you could say, because, I smuggled in the affine selection. Right? So if you don't have affine selections, then things get a little bit more iffy, meaning very often we cannot do the fold. And it's not a panacea. It does not always give you the best performance. But for many cases, we have shown that it gives you so good performance that, unless you really need a black belt programmer that gets the last 10%, you can prototype things very quickly and get very reasonable performance.
It is kind of funny because the comparison you're drawing between the libraries and the SAC compiler is actually kind of the opposite of the comparison that I often draw between C and APL, which is that the advantage of C is the same as you described, where you can fuse all your operations together. The advantage of APL is that you have these handwritten kernels for things like, if somebody does a plus scan or some sort of transpose, you'll have a handwritten kernel that's designed for that operation specifically. So, of course, the direction I always present this in is, C is always presented as like the fastest thing, but APL can actually be faster than C. And you're going in the other direction of this, and I totally agree with you. This fuse everything model can also be faster than the library model. So it's kind of interesting that it's the default assumption in a lot of places that, you just can't beat fusing compilation. And in other places, the default is, you just can't beat these libraries.
I beg to differ a little here. I think we may have to look at it at a little bit closer perspective. Yeah, sure. If all you want to do is a certain operation or a certain set of operations, you can tune them to a level that is outrageous, and you get this is what I typically refer to as the black belt programmers. If you speak to an HPC person, they don't buy into any of what I'm saying. They say, I have to be in control of the assembly that is being, if I can't do this, I'm not interested. And yeah, sure. The question is how what happens if I don't have a black belt programmer that I can or want to pay for this, and how far do I get? And yes, if your applications always only use I don't know, the 40 or 50 combinators that you may have in your favorite array language, then maybe you can get very good performance, and individual operators most likely will beat anything that we can generate by miles, at least a solid percentage. I agree, and yes, that is true. But the question is, what happens if, how many combinations of phrases, I think you call this a dialogue, do you actually recognize? And what happens if somebody is using a phrase that is not recognized by the compiler? Because I know, for example, I was talking...
Then you're in trouble.
Yeah, you're in trouble. And I have seen this at work. I mean, I know Bob Bernanke quite well, and I spent quite some time with him. And, he did a lot of consultancy in APL. And one of the things that he did, he says, look, what they have written here. No, if we write it like this, then the phrases will be understood. And then, wow, et voila, factor of 8. And this is great. But if you don't have your Bob Bernanke on your belt, then it's a bit harder. And I think this is the same here. Yeah. I think it really, and another thing that is I think is important is that you don't have to rewrite things if you go from one architecture to a new one.
Well, no, that's an advantage of both systems.
Well, yeah, that's an advantage of APL in the same way as it is.
Yeah. So, I mean, if I can give a little more organization to it, your black belt programmer who's working on your specific problem is not actually either of the things I'm comparing here. I mean, I agree. You know, if you have a programmer that knows the specific hardware, that knows the problem, that's able to tune it, that's just the fastest that you can humanly do. So the two different possible compromises are to have, you know, a compiler like C or SAC, which uses very general mechanisms, but might not always be able to compile them that well, versus the library or APL model, where you have specific operations that are definitely optimized well, but may not be the ones that you want. Neither of these is the ideal, and you get different trade-offs and different properties with both of them.
Yeah, I completely agree with you. Absolutely right. I subscribe to that. What I have difficulties with is if you say, well, a compiler like SAC or C. When I started out,
I don't. These are in the same category, but they're not the same thing.
Yes, and it is. You would be surprised. I mean, I was surprised very much when I started out. I thought, yeah, hey, I'm using C, a subset of C, so maybe I can make it a preprocessor, right? I just, strip away the stuff and then give it to C. And then I found out that the C compiler couldn't do much with it. Many obvious optimizations were just not possible. And I thought, wow, why is the C compiler doing this? And then I got into a European project which, amongst other things, had a C compiler company from Amsterdam, and they were called ACE, I think, in the consortium. And I was talking to these guys. I said, why don't your compiler do this? And his answer was, we can't. So, why can't you? Well, because we cannot guarantee that this is actually semantically sound. Because we don't have a guarantee that, there is no side effect. We don't have a guarantee that someone relies on this pointer to exist. And it is really amazing if you look at what the C compiler should be doing and you would expect it to do, it very often does not do. For good reasons, because people rely on the semantics of C, whatever that exactly is. But so, one of the beauties of using something like SAC is that we cut away the semantic ambivalence. So in SAC, this I can give you like 2 pages of a semantics description, and that's it. That's what the compiler is supposed to do. There is no such thing as, if you do this, then it's undefined behavior. If you do that, then only this is guaranteed, and this may or may not happen. And there's a good reason that I think the C99 standard was already like 300 pages. And that is a problem that makes compiler life hard. I think the approach that C takes, and which is very successful, don't get me wrong, right, is we give you a super cool macro assembler, and it maps all down to the hardware very efficiently, and you deal with anything that comes on top of it. Whereas the second approach is, okay, we give you a clean language that is completely decoupled from the hardware, and we try to create a relation between the two by generating C code that hopefully does what we have promised you in the semantics. But having this on the high level, we can do optimizations that other compilers can only dream about. So if you give me an expression like any function f applied to a x b c, and you have the same syntactically the same thing a little bit further down, I know it's going to compute the same thing. I can throw one computation away. Common sub-expression elimination, et voila. And that is something that the C compiler never can do. And so the constraints are very different. Our pretense to be C is maybe misleading sometimes. So people think, they just hand it over to C. It's just, but it turns out, all the optimizations that you typically have in a C compiler, we had to implement as well, because we can apply them way more radically. That was the first, painful lesson that we had to learn very early on. Who would think that I have to implement something like variable propagation, common sub-expression elimination, loop unrolling? The C compiler should be able to do that as well, right? It turns out no.
Is that the default backend then? If you don't specify the GPU or OpenMP, does it compile or does it generate C code and then compiles that? That's the default?
Yeah, that's the only way. So we only create C code. All our optimizations happen on a very high level, almost on source level of SAC. So you can if you download the compiler, install the compiler, or run the compiler, you can break it after all the phases, and you can kind of read the SAC code that the compiler has on between. And only in the very out of, I don't know, the 60 phases that we have in our compilation, only the last 4 or 5 really go down to C level. And we also create CUDA code.
Yeah, well, because why would you ever introduce pointers to something? If you have a representation without them, you're just immediately giving up so much.
At a certain point, you have to, right? I mean, if you
oh yeah, eventually, yeah. I mean, because the CPU works with pointers, but yeah, delay it as long as possible.
Yes, absolutely. Yeah, we stay functional as long as possible, and all the misery starts when our memory phase kicks in, and we say, oh, now we introduce the notion of memory, and oh, now we have sharing and pointers and reference counting, and now we cannot do anything to the code anymore, really. Nothing really meaningful.
Was there, and this is an odd question, but was there any consideration of alternative names that were more indicative of the functional array? Because single assignment C, the first time I heard of it, I was like, that's an array language? Because it sounds like a kind of, there's a bunch of C++, and obviously that's less well-known than C++, but single assignment C is in the group of modified C, So I'm just curious in the back, because I know other, languages like Futhark that are kind of Haskell-esque, they have and I think they've got a hedgehog for their logo, whereas for those that don't know, the logo for single assignment C is a C with a lambda up in the corner. So the logo is very indicative that there's something functional going on because there's a lambda there. But anyways, curious if there was alternatives that didn't make the cut.
No, not really. It was. I kind of liked C because you can tune the performance, and it stinks performance kind of, and it needed to be short. I was also very inspired by Sisal at the time. I don't know whether you guys are aware. It was single assignment in this streaming array language. It was a project from LLNL and Lawrence Livermore. And so that was also, in a way, very similar to SAC, but not rank polymorphic at all. It didn't have any of the array stuff. This came just in because I was a spoiled kid, right? I come from functional programming, so I want nice and beautiful abstractions that I can just put together. And so obviously, dealing with more down-to-earth, fixed dimensional arrays was nice. But they also had these data parallel combinator construct. I have forgotten that we called kind of a for each construct that they had. And I thought this is a kind of a cool name. And then I thought, okay, single assignment is indicating that it is functional, but it's also not completely. So then, if it sounds like C, maybe they're inclined to try it. And if it would have been something more esoteric or let alone Haskellish, then people might think, oh my God, I need to learn about monads, and I don't want to learn about monads. And I don't know. It definitely has not paid off in terms of having 10 million users. That's what it is. I'd be happy to. But I think it is actually what I still like is this stupid insight that most likely is clear to everyone but me, that C is actually a rather functional language. The amazing thing is you throw away pointers, the notion of memory, you throw it away, and it's totally functional. And you start if you start teaching, for example, smaller kids, you teach them programming. How do you start teaching programming? Oh yeah, you write functions, yeah, and then you pass on scalar values. Sure. And then it behaves like math. It's easy to understand. And it's all clear. And, as soon as you start talking about, oh, but now we have to allocate memory, the whole world breaks down. And that's what it is. So, yeah, I don't know. If you have a better idea, we can't rename. I'm open to anything.
I do not. Maybe the chat GPTs do, but but we'll put a pin in that topic. The other question I was going to ask was, so you mentioned that you were working on functional languages, and then you basically had kind of the performance insight from a student mentioning the C. And then it sounded like you just stumbled across Lenore Mullen's Mathematics of Arrays work. Up until then, like, had you been exploring the, I guess, array languages? Like, had you heard of like APLJ, or was it just this, Mathematics of Arrays? You found yourself reading it, and then that kind of combined with the C, like you were off in a new direction at that point.
Yeah, it was kind of a gradual thing to happen. So I looked at. I said, okay, this kind of typical task parallelism that the functional guys were doing at the time, I thought is way too hard. If the sequential performance is not up to speed, I don't need to talk about speed ups at all. It's useless. So I have to have a sequential thing that is fast enough. And then the question is, it has to be not task parallelism, because task parallelism is really kind of bad, because it means that you unfold the parallelism only gradually, exponentially, but the organizational structure is horrible, and then you have to fold the parallelism back together, and so I thought, okay, we have to do something like data parallelism. And then I heard of Sisal. I thought, Sisal, they have good performance and they look rather functional, actually. That is interesting, but it's not really that beautiful, and is also being done already. And then I think my PhD supervisor actually visited a colleague in Berkeley, and this colleague was, I think, in the committee of Lee Mullen, and so that's how her PhD landed on my desk. And he said, "Oh, Bodo, I saw this stuff, and I thought, you are interested in data parallelism, and you're not so happy with the beauty of Sisal. Maybe this is more beautiful. Have a look." And then I got into this and I started reading up on this. I thought, this is actually quite interesting. This is very beautiful. And from there, I got pointers to APL. And then I started realizing, there's a relationship between this. And then I thought, if I can do this with loopy thing, maybe I can speed up APL. So I wrote in 98 or something, I wrote like accelerating APL programs with compilation to SEC or something like that. And that's how I got in touch with Bob. And Bob kind of inundated me with the how should I say, the dogma of APL, which was good. It was being showered with this over and over again. I thought, okay, I start getting it. But it took me another, I don't know, couple of years to really appreciate this approach and understand this thinking in terms of shapes and traversing ranks and these kind of things, and that was very helpful. But no, it did not come through my educational stream or something. It was more or less coincidental through the back door.
I was going to say that's probably one of the most unique stories of like the path to array languages and APL is just basically having it was your PhD advisor that was on a trip that bumped into similar work and then brought it back, and then you I would think of that as a little bit backwards, and then later on you discovered APL.
Yeah, but you see, it was the late 80s, so the internet had just was in its infancy. So it was not like, you would typically have to go to a library to find things, or you have to go to a conference, to get hold of the proceedings and things like that. So, today it's a different story. You hear something, you just Google it, and then you have, try APL in your browser, and there you go. But in those days that was different. So, it was interesting.
Yeah, I totally wasn't thinking about that fact.
Sorry, I'm a bit of an old bloke.
When we talk to folks, a lot of them, they say they will have had a course that was taught in school or something on APL. But yeah, I guess you have to keep in mind that there is a like pre-internet era. Sure. That was, I mean, most of my life was you could just Google stuff. But yeah, and if you don't have a course in university, how does one come across APL? You basically have to bump into someone like that knows about it. Otherwise, it's not like you're going to read about APL in the newspaper.
And I think actually APL is it's more like something that had grown in the US and was more widely spread there and had made it to the UK, but continental Europe, I'm not so sure. At the university that I was studying, there was no one who knew anything about APL. So after I had started talking about this, people started asking me, which I found funny. But well, today I could help out. But even here, there was nothing in the curriculum at the time. Even now, we don't teach APL here. So I think it's in particular continental Europe. I don't think it's done so much. I'm not so sure about the UK, whether that is taught very often. I've been working in 2 UK institutions and both didn't teach any APL. So I don't know. I think it's more of an American thing, maybe.
And I guess the other area that I've seen people come through from doing these interviews and the episodes we've done is that they go to work someplace that uses APL, and then they're mentored with somebody else that they sit along beside, and that's how they pick it up. And that's not a way to build out your user base really quickly. It's one-on-one for a while, and then, I mean, it builds deep, but it doesn't build broad as much. I think that's changing, but I think a lot of the history of people comes through that way.
Yeah, I think that happens with many languages. I mean, that's the other thing. There's so many languages out there. And so I think it's actually very exciting to see that there is multiple different approaches to array language, like, for example, Futag or Accelerate, the Haskell guys here from Utrecht as well. Yeah, that's exciting. So we actually submitted a paper that compares Futag to Accelerate to APL dialog and SAC. And so we looked at a couple of applications and looked at the performance that we would get on shared memory multi-core systems and GPU systems from the same sources. And that was, we also had DACE on board, which is also quite an interesting development.
Sorry, what was that a different language, DACE?
DACE, yeah. It's an annotation language developed by, I think, the group of Thorsten Höffler and ETH Zurich. And they come from the high performance computing thing. And the idea is really just you annotate your code, and then the compiler can parallelize it for you. But it's also based around this idea of shapes and dealing with shapes. But most of these languages are actually not ranked polymorphic. Too bad.
And is this paper already published, or you said you just submitted it?
Well, we submitted it a couple of months ago.
The preprint is out, though.
Okay. The preprint is out, then we will link it in the show notes for those. It does sound like an interesting read.
That's true. We put it on archive, actually. I was just wondering what preprint are you talking about, but then we put it on archive.
Didn't hallucinate it.
No.
Stephen, I saw it looked like you unmuted your mic, so I'm not sure. I could be hallucinating, but if you did, feel free to ask your question.
You are not an AI, and you are not hallucinating. No, I'm picking up on the discussion of languages a moment ago. On your website, Bodhi, you say that SAC is predominantly suited for application areas such as numerically intensive applications and signal processing, and it's that kind of high performance ballpark that we've been talking about today. But I wonder, do you yourself use it for anything else? Should I think about making it my go-to language for general hacking?
Absolutely, you should. No, obviously not. So one of the things that we, as I tried to explain in the beginning, the motivation was to say, okay, I sacrifice many things that are dear to me, like higher order functions, complicated polymorphic type systems and things like that, for the sake of being able to get performance, because performance was a kind of a key selling point in my view, or the point that interested me most. Let's put it that way. So we have a couple of restrictions in the language that, like higher order function. Yeah, it's painful, but okay, you can live with it. Polymorphism. Yeah, it's not nice, but okay, you can live with it. And one of the things that is not so nice is that our arrays have to be homogeneously nested. So you can nest arrays, but we implicitly consider them higher dimensional. So if you have a 10 by 10 array of 10 by 10 matrices, then it is implicitly a 4-dimensional 1 by 10 by 10 by 10 by 10. But this only works if all the elements of the 10 by 10 outer shell have the same shape, and that is kind of painful. Now, because if you want to, for example, you want to do some text processing, then you have a bit of a problem, unless you start padding your values, which I think is a little bit kind of, it could be done, but it is not exactly my beauty ideal. And so we don't have the generic form of nesting that, for example, APL offers, and that is a major constraint. Likewise, we do have structs now, so you can have kind of collections of non-homogeneous items, which, by the way, we compile away completely, so in the backend they don't even exist. But this is only possible if you do not allow for them to be recursive. You cannot do something like a linked list. So I think it is a bit painful. Another thing that we do not really support very nicely is streams. But that is something that I hope to work on over the summer when I'm doing a sabbatical in Japan, and hopefully we will look into infinitely dimensional arrays. So that's something that I spent some work on a couple of years ago, talking about transfinite arrays. And then, you could have an array that has the shape omega omega. And then you can start thinking about, specificationally, this is super beautiful. And, theoretically, you have all the nice properties that you want to have. But implementing is a bit of a challenge, and implementing it efficiently is an even bigger challenge. And so we will start looking into this over the summer. I think this is some work that had been Bob pointed me to a paper by one of the early pioneers. I forgot his name. That was
Alan Perlis, maybe?
Who?
Alan Perlis.
No.
He did write about infinite dimensional, I don't think he ever did infinity in more than one direction, but he wrote one paper about infinite dimensional arrays.
Yeah, but so it is. I'm quite enthusiastic about that. In particular, what happens if you cannot decide how long they are, because then your entire memory management, the kind of code that you need to generate, is very different. And it's the kind of code that you would like, for example, to generate if you run things on an FPGA, because FPGA gets its performance by streaming the data through it. So that means if you have even a normal SAC program as it is now, you need to transform it into a streaming variant. And if so you have to understand the relationship between finite size arrays and infinite arrays kind of better. And I think, on the theoretical level, we have understood this, but on an implementation level, it's harder, way harder. But it's not a go-to language for everything, I guess. And look at the Apex compiler of Bob, and you see, you can write a compiler in APL if you want to, or Aaron's GPU code generator, the same story, and it's beautiful. But it is kind of also a little bit unconventional, because the data types that you use are different. And many of my colleagues also ask, when are you going to re-implement the compiler in SEC itself? And I don't think anytime soon. If somebody else wants to pick up on that, that's great. And I would, be happy to share any insights in where not to go. But having more dynamic data types would be most likely desirable. But if I wanted to do that, I would have to spend the rest of my career on that. And I'm actually a bit more selfish, and because I'm interested in high performance code generation and parallel architectures. So this is what I will focus on. If there's a young colleague that wants to go for this, I'm more than happy to.
I was going to say that's one of the advantages of being the explorer. You get to choose where you explore.
To some degree. You also have to find your funding, right? And so you have to, be able to identify where in the spectrum you are and how big tech can possibly benefit from what you're doing. And that is not always easy, in particular, if you don't do mainstream stuff. And people say, that also would be great, to do. I'm always trying to find a company that is, should I say, bold enough to use our technology for real, because then we could potentially get a little bit of money to stabilize things more and to do more development, which is not exactly immediately academically publishable. Because it's always, the entire maintenance work is mainly done by a couple of colleagues that, burn their midnight oil every now and then. And, we have fun in doing that. That is true. But it would be nice if sometimes would not have to worry about the next grant proposal.
It's a different level of implementation challenge.
Yeah, you have to, some of the code is, oh my God, it's open source. If you want to see some very dark corners in the universe, you can dig through our code base. I will promise you there are also interesting Easter eggs, comments like, yeah, I think this should be done differently, but I don't have the time to do it just now. Or like one of my students coming in the other day and said, oh, Bodo, I saw here, I looked at Git blame, and the code was written before I was born. And I thought to myself, damn.
Must have been some good code to last so long.
Well, no. It's just the code kind of does it, and don't change your running system.
I was going to say, speaking of corporations that may or may not want to use SAC, where should we be sending listeners / potentially companies that are looking to use SAC? Is it the main landing page? I can't remember if it's sac.org or
SAChome.org. Yes, definitely. I mean, I know it would be nice to freshen up the web page, but hey, or contact me directly if there's anything that they are missing. Because it's our main effort really goes in the development of the system and the advancement of the system, not necessarily in its advertisement, in selling it, or getting. I know this is from a business perspective, this is a stupid move, but I think most of the contributors are just too curious, and they are more curious than trying to make it a lot of money, because it's a very difficult business. And once you start getting money for this, you also have other obligations, and I think it's become a little bit more serious on certain aspects. And I think I kind of would be intrigued to try that out for a while if there's an opportunity, but it would have to be an opportunity that does not require me to make an upfront investment of a couple of years with a couple of PhD students or ex-PhD students, and then put all the eggs into that basket. So it would have to be someone who comes along and says, okay, I'm interested in this technology, and as is, I can use it as a starting point, but I need some security in terms of stability, and I'm happy to give you some money for that. That would be a starting point that would be great to develop this further and make this happen. But without that, I think it is not really thinkable. And people are always kind of, they are concerned, and they then say, oh yeah, but will you exist in 10 years' time? And that's dangerous and difficult, and I don't know. So you have to find this one customer that is really keen to use it, and then say, well, we have a BSD-like license, so it's not that there's anything that we will hide from you. So I think the risk is reasonable, but it has to give them an added advantage. And so in a way, I think what could become a well, maybe kind of unique selling point is if our type patterns are really going to be everywhere. And this is what we are currently pushing for, so that you can actually provide all kinds of guarantees about your domains and the shapes of your arguments. And you say, okay, these two arguments have to be in this relation, and the values have to be in this relation. And you can plug in any function that you say, oh, this is a precondition for this, and this is a postcondition for this. And that, I think, would give people that, for example, currently go to NumPy or something like that, and that would give them a bit more of a guarantee and more confidence in the correctness of their code. Now, as soon as you start playing with crazy shapes and higher dimensional shapes like this, like 10-dimensional arrays, you really want to specify what you expect, and you want to see when you break this kind of envisioned condition or the requirement that conformity that you expect when you call it, when you envision a certain conformity in the arguments or a certain value to be in a certain range. And if you call it wrongly, you want to hear about it and say, so this function actually requires, say, the second argument to be an odd number, and I have given it an even number. Oh, maybe that's not a good idea. And then you can, I think it will greatly improve the trust that you can have on these applications. And it's also interesting research in this context. So one of my ex-PhD students is now a lecturer in Southampton, and he's very much interested in specifying these things in Agda, which is a dependently typed language. And there you can prove all kinds of things. And so he also has a code generator that generates SEC from his Agda specifications. So then you can write an Agda program where you can have all the dependently typed security in the world, and then just crank out SEC code, and then it gives you hopefully the performance you hope for. But then you have static guarantees of the properties, which I think would be taking it to the next level. And I think there's actually I also saw recently there's a paper from St. Andrews, the Idris group, which are also interdependently typed, and they try to go a little bit in that direction as well. I think with this hype around machine learning, there's quite a few people that actually may want to have this. And so maybe there's an opportunity. We shall see. We shall see.
And I just realized, too, that not just the standard library is open source on GitHub, but on GitLab, the compiler is also open source. So if folks are listening to this and are either want to go look around or want to contribute, is it because obviously I know there's a bunch of PhD students that are doing work on this, but if folks out in the wild are interested in adding some backend or making some contribution, is it open to contributions even if you're not doing a PhD?
Absolutely. Yeah. Absolutely. Yeah. Now we don't host it on the public GitLab server because we are kind of a little bit afraid that at a certain point GitLab may say, okay, if you want to continue using our service, you will have to pay. And so we run a GitLab instance on a service where we pay a couple of euros every month. So you can subscribe to this GitLab Sec Home org. And then, let me know because I have to kind of approve this thing. And where there are so many spam attempts that I typically tell everybody, if you really want this, drop me an email, and then I give you access. Like, you can just fork it off and create your own branch. You can create a merge request. You can raise issues, anything. And we try to even react on issues and fix bugs if they come along, or we have also some discussions. I think the access is anyways open, so you can actually look at the sources straight away and play around with them and see, scavenge for our Easter eggs.
Awesome. Well, we will make sure to leave links to the sachome.org website, the GitLab, because I had poked around and I didn't realize that the compiler was just on a different site. Yeah, gitlab.sachome.org. and also to the SACPace
Mhm.
GitHub page, which has the standard library and demos and stuff like that.
Yes, and that's just box standard. The standard library and all that is just on the standard GitLab thing. Because we do all the CI/CD stuff that we do on our own GitLab server, because that's our main concern. That we have, if we have typically like 10, 15 merge requests that are open, and we run pipelines that run for several hours on like 10 different platforms. And if we would have to pay for that on the GitHub server, then we would very quickly run out of money. So that's why we say, no. We run this on our own service, that's fine. And the standard library is just on GitHub.
Well, I think we'll say thank you so much for spending your time with us. This has been a blast. It's been awesome to learn. I mean, I've always been SAC curious. As I mentioned 2 or 3 years ago, I dove into it a little bit, and I think I wrote, I don't know, maybe 100, 200 lines of SAC code and just mini examples. And yeah, it's super awesome to have you on the podcast and learn more about it. We will say that if you have questions for Bodo or for us, or if you got comments, feel free to reach us at
contact@arraycast.com. And I started this off by saying I was ready to have my mind expanded, and I certainly have, which is really... that's what stretching your mind feels like, I guess. There are times of confusion, there are times of recognition, but that was, I really enjoyed this. This is really interesting to look at, and especially the rank polymorphism. I think that's a great example of how it can be used, and make a real strong case for it. And I imagine there may be languages that don't have it that now are wondering about that decision, because it does seem to me to be a very strong thing that you can do when you can break a problem up like that recursively. Anyway, thanks so much as well for coming on. And that's it. Contact@arraycast.com if you want to get in touch with us.
Yeah, thank you so much for having me. It's been an absolute pleasure, and I could, keep chatting to you guys forever. And the same holds, for me. Anyone who wants to contact me, feel free to do so. I can be easily found either on the SEC homepage, www.sec-home.org, or just directly Google my name and you'll find me. Drop me an email. I'm always happy to have this kind of chat or any other chat, and I would be keen to have new collaborators contributing to the project. Sorry for the plot. I couldn't resist.
That's what we're here for. Thanks. Yeah, once again, this has been awesome. And with that, we'll say happy array programming.
Happy array programming.